All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. I think last time we were doing some related rates problems, and we have like one left. So let's actually just finish that up and jump into the next topic. I mean, the responsible thing to do would be to do a small recap, wouldn't it? Okay. Let's look at what we looked at last time. Yeah. So we looked at the topic of related rates, for which we need to remember how to do implicit differentiation. Related rates is just a process of figuring out the rates of change of some quantities that you don't have information about their rates of change directly. Instead, what you have is some related quantity, and you know the rates of change of that. And it turns out that when quantities are related by, say, some equation, then their rates of change are automatically related by differentiating that equation implicitly. And so by finding out, by being given information on the rates of change of related quantities, we can figure out their rates of change. So we know we're looking at a related rates problem if the word problem you're looking at does this, right? You're going to be told about related quantities, and you're going to be given the rates of change of some of them, and you're going to be asked about the rates of change of some other one. And then once you know that that's going on, you're going to go through this 6-step process, always this 6-step process, always in this order. So it's just something for you to know. Okay, so one thing I would like to remind you is that it is always with respect to time. Always. T is the independent variable. Always. Okay, do not forget that. So if you're looking at a related rates problem, the T is the independent variable. Okay, so you're always differentiating with respect to T. So the steps are to read the problem carefully, know what's going on, draw a diagram if possible and necessary. Be sure to label things that are changing with variables, things that are not changing with constants. The point of drawing the diagram is to help you come up with an equation that's going to get you to the answer. If you're given an equation, you don't need the diagram. We had an example of that where we're just like, oh, we can skip the diagram step. You're going to write down what you know, write down what you want, write down the rates you know, write down the rate you want and at what position that you want it. Come up with the equation that your diagram may have helped you with. You're going to differentiate that equation implicitly with respect to time. Then you're going to plug in your knowns and solve for your unknowns. In case you do not have all the information by step 6, you may have to go back to step 4. To find all the unknowns. So you get to the last step, you don't have everything, don't panic, just go back to step 4, figure it out. And at the end of the day, doing that will get you to your answer. So it's always that 6-step process. We did a bunch of examples going through that. So you see it's the read, diagram, what you know, what you want, equation, differentiate, plug in. Read, diagram, what you know, what you want, equation, differentiate, plug in. In this case, we have to go back to step 4. Read, diagram, which is not necessary here since we're given the equation. What you know, what you want, equation, differentiate, plug in. Read, diagram, what you know, what you want, equation, differentiate, plug in. Read, diagram, what you know, what you want, equation, differentiate, plug in. Read, diagram. Oh, I'm not sure what was going to come next. Oh, what you know, what you want. Surprising. Equation, differentiate, plug in. Right? That's it. All right, cool. Left you with one last example. What did you guys get here?
I got, like, for the answer, I got 360.
Okay, so we have a guess here. So we have a guess 360. Let's see. All right, so geez, how do I do this again? Yeah, if you say that with a related rates problem, you done messed up, right? You should always know what to do next. It's a predefined process for you. Okay. First thing is you always read, right? You need to recognize it's a related rates problem. You need to know which numbers you want to pick out, how you're going to start setting things up. Reading is also going to help you set up that diagram. Okay. So let's read. Superman is cruising at 390 feet per second at an altitude of 5,000 feet. He flies directly over Jhevon's house. Does it all the time, every Sunday. Assuming Superman's altitude and speed is maintained, right? How fast is the distance from the house to Superman changing when Superman is 13,000 feet from the house? Interesting. Okay, so here's the ground. Here's Jhevon's house. Jhevon's inside minding his business, probably teaching a class. Right. So this is Superman. Superman's trajectory, flying over the house. Here's Superman. He happens to be here at this point, but he's flying in this direction. Okay. We do know he is at an altitude of 5,000 feet. And what do we know? Okay, we care about the distance between the house and Superman. And again, in math, distance, we're always talking about the straight line distance unless otherwise stated. So we care about this distance right here. And there was a point where Superman flew directly over the house. So at one point he was here, that was 5,000. So I can measure, say, the distance between when Superman originally flew over the house to where he is now, as at the point where he's 13,000 feet away from the house. Okay, so now obviously here we have this little upside down right triangle. Let me label these guys something. So, or I'll label in the next diagram. So this here is the distance Superman covered since flying over the house. This is the distance between Superman and the house. Okay, so that's me. After carefully reading the situation, seeing what's going on, I can now come up with a diagram that describes the situation. It's this upside down right triangle where the height happens to be 5,000. Now, the top part of the rectangle, the length, the horizontal length, is it's changing, right? Because Superman is moving. In fact, it's getting bigger. So I'll label that with a variable because that's changing. The 5,000 is not changing because he's maintaining altitude. And the distance between Superman and the house, well, that's y, isn't it? Right, so that's also changing. In fact, that's also increasing because it gets longer the farther away Superman flies. All right, cool. So that's our diagram, right? And this is me reading the problem, kind of slowly figuring out the situation. Yeah, so that was diagram. Now 3. What do we know? What do we want? So I know how fast Superman is cruising, 390 feet per second. That's going to be the distance at which x is increasing. And what do we want? How fast is the distance from the house changing when Superman is 13,000 feet from the house? So we want dy dt when y equals 13,000. So when the distance from the house, which is y, is 13,000, at that point, I want to know how fast is y changing. All right, cool. 4, we're going to come up with an equation. What's the equation here?
X squared plus y squared equals z squared.
There's no z.
Oh, sorry, equals wait, the way I set this up was different, but
Okay, yeah, just look at this diagram. Shouldn't be hard to set it up again.
X squared plus y squared equals 5,000 squared.
No.
Or 5,000 squared plus x squared equals y squared.
Right, the y is the hypotenuse, right? So y equals x squared plus 5,000 squared. Okay, so that's our equation. 5, we are going to differentiate. So we're going to have 2y y prime equals 2x dx dt. In fact, I can divide both sides by 2, and I can move the dy dt. Well, move the y, right? Because that's the guy we want. All right, so now we go on to step 6. We are going to plug in. And so we get dy dt is equal to x. Were we told what x is? How far is that horizontal distance? Well, dx dt, we know that's 390. And y, we know that's 13,000. We do not know the x. What do we do? Panic. Gonna fail this test. My parents are gonna disown me. I'm not going to get into med school. No, you go back to step 4, right? Do not give in to the despair. Do not, no matter what. Okay, so back to step 4. Remember that the despair is a self-fulfilling prophecy. Don't go there. Just don't. No matter how dire, don't let your mind go there. All right, we go back to step 4, which is this equation. So we know that y squared is equal to x squared plus 5,000 squared. And we know that our y is 13,000. Now, one thing you can notice is that this guy is 13 times 1,000. So your 5,000 is 5 times 1,000. So what must your x be? This is another one of those special triangles, actually. Those special Pythagorean triples. Hypotenuse is 13, one leg is 5. What must the other leg be? That's right, it should be 12. Right, so this is the next most famous triangle, I think. So we have the 3, 4, 5, and everyone beats that one to death. But there are a couple more that are very common, and it's a 5, 12, 13 triangle. 5, 12, and 13 go together. So 5 squared is 25. 12 squared is 144. Take 25 plus 144, you get 169. 169 happens to be 13 squared. So 5, 12, and 13 go together. They're Pythagorean triples. 13 would, of course, be the hypotenuse. So this is something that you could know. So you won't have to like be squaring 13 or whatever. Or at least if you look at this, I would probably figure out the relationship by squaring the 5 and the 13 and then solving for, you know, the square root of the 13 squared minus the 5 squared. That would be easier. But yeah, that's the thing. So here it means our x is 12,000. Now we go back to step 6. Where we left off was our dy dt. T is always the independent variable, is x, which we now know is 12,000, times 390 over 13,000. So of course the thousands cancel. 13 actually goes into 39 3 times, so that goes into that 30 times. So we actually have 12 times 30. 3 12s 36 times 10, 360. And this is feet per second. Right, which is what we guessed. Or what Sarah guessed, I think it was Sarah. Yeah. So yeah, read, diagram, what we know, what we want, equation, differentiate, plug in, right? Same thing. And last time, by the way, these last two problems, the 8 and the problem that we just did, you know, those are like test or final problems, right? I mean, the other ones are like, the ones we did before was like stuff I could put on a quiz, right? It shouldn't be that bad. I think I put a very similar problem on a quiz before. But yeah, remember we had many other things we could practice, right? So we didn't do problems 2, 6, 7, 9, and 11. You can take a shot at them. Can do more problems in your textbook. Also for the homework. When I post the homework, did I post all of chapter 4 homework? I should look. So yeah, practice a lot. It's always the same process, but the creativity might come in the setup, particularly in parts 2 and 4, to kind of be able to draw a diagram to describe the situation and then come up with an equation. Those are going to be the hardest parts, but they still all fall into a very predefined set of rules. All right. That being said, it's kind of all I wanted to do as far as related rates are concerned. We did tons of examples, and it was really just an illustration of the process more than anything. So now what we want to do is move on to another topic, a very important topic. We are going to talk about maximums and minimums. Now, I understand you might think we already know everything about maximums and minimums because we already did the first derivative test. But the first derivative test, make sure the scale is same here, because sometimes I start writing big. Okay. But the first derivative test can only find what we call local maximums and minimums. We might care about maximums and minimums in a more general sense, let's say. So we're going to talk about max and min values in a more general sense. And this is the subject of section 4.2. Max, short for maximum, and min, short for minimum. values. Okay, so we're doing max and min values. Okay, cool. Have to start out with a bunch of definitions here to let you know the differences between the kinds of max and mins that we might be interested in. So yeah, let's start out by saying that f of x be a function of x. Let I be an interval on the real line. Okay. Here are some definitions. Definition. We say f of x has an absolute or global max at max in I at x naught if so we can say, oh, this function has an absolute max on this interval. We just say on this interval. I mean, in the interval is can also work, I think, but we usually say on. We can say the function has an absolute maximum on this interval. And what we are saying when we say that is that the output at that value is greater than or equal to the output of every other value in the interval, right? So that's the absolute maximum. That's the biggest it can get, right? On a global scale, right? So we sometimes call it the absolute max or the global max. Mostly absolute max. I'll mostly use the phrase absolute max, but if you see the word global, you shouldn't be confused. Yeah, so you're the absolute maximum. You're the absolute maximum output if the output at that point is greater than or equal to every other output on the interval you're considering, right? Okay, cool. Similarly, we say f of x has an absolute or global min on I at x naught if the output there is smaller than or equal to every other value. Okay. So that is your absolute max and absolute min. Pretty much, these are the biggest guys around, right? The largest and smallest values, respectively, on the entire interval. Like they're larger and smaller than everyone else, respectively. Now, to talk about local max and mins, it's going to be a very similar idea. In fact, I can sort of copy these down. So now I'm going to define a different kind of So now we're going to define a different kind. So absolute max, absolute min. Now we're going to talk about something called a local max. Another word for that is relative max. If this is true, for all x, so it's not all x on I, it's for all x near x naught on I. So it's not for everyone in the interval, but it's for everyone close to the point that's in the interval. So near is a very strange phrase. I should define that pretty soon. But similarly, we say it has a local or relative minimum if this is true for all x near x naught on I. Near. So near is kind of funny. What it means when we say near x naught, it means within some small open interval centered at x naught. Okay, so pretty much you go to x naught, that x value, and you open up a very small window. And then you look at all outputs within that little tiny window. And if the output at x naught is bigger than everyone there, we say it's a local maximum. It might not be the biggest on a global scale, but it's the biggest guy in his like little neighborhood, right? In his neck of the woods, he's the biggest guy around. So you open a very small, tiny window. And you check if that point is bigger than everyone. And if it is, we call it a local maximum. Similarly, if we open a small, tiny window around that x value and we realize the output there is smaller than or equal to everyone within that small, tiny window, we say it is a local min. Okay, so that's just the definitions, which I'm going to illustrate them to make it more clear what the difference between the two are. These guys kind of off. Okay, cool. Let's talk about some other stuff. Some more language, I guess. Note, max and min points are also called extreme points. The plural of extreme point is the phrase extrema. Right, getting right. So saying absolute extrema is the same as saying absolute max and min points. Right. So you'll see it in your homework, your textbook. They'll sometimes say, oh, find all the global extrema. And you're like, what is that? They're just talking about find all the global maximum and minimum points, right? Extrema is another phrase that we use. Yeah, that is the terminology. Now let's actually illustrate. Illustrations, hopefully helpful. To kind of tell the difference between the two. We are going to have a key here. So let me say here, AM is going to be short for absolute max. Little am, short for absolute min. We're going to have LM, short for local max. And little lm, short for local min. And I want you guys to look at these illustrations. Okay, so and draw a bunch of functions. We're going to identify the max and mins here. I'll do 6 examples. Okay, so what will always be in play is your A and your B. So that's the interval we're looking at, the interval AB. Okay, so here's the first picture. Oh, come on, iPad. The second picture. This point happens right above B. Okay, so that's the second picture. Third picture. We also have this little thing. And it goes like it's going up. This case we have and our graph looks like this. And this one. Okay. And this one. Okay, we have all of those. All right. So we're going to go through with all of these guys, and our goal is we're going to identify the absolute maximums, absolute minimums, the local maximums, and local minimums. right? So just to make sure that we fully understand like what we're talking about. Okay. So yeah, identify where these guys are going to be. So for the first one, top left, where are is there an absolute max on AB? We want to identify these on AB, on the interval AB. All right, does this guy have an absolute max or an absolute min? Absolute max, yes or no?
Yes.
Yes. The absolute min, yes or no?
No. Wait, yes.
Okay. So the absolute max is here, right? Right on the pinnacle, AM. The absolute mins are over here. They're at the base because they're included in the interval, right? The circle is shaded. I will make another note here, just so we're clear. An absolute max or min will automatically be a local max or min, but not the other way around. So absolute extrema supersede local extrema in the sense that if a point is both, we call it an absolute extreme point. Because in that case, local would be implied. So here, yes, it's an absolute maximum, but it's also local, right? Because if I were to open, if around that point, which is the X naught right here, if I were to open a little tiny window and just kind of focus my vision on that, pretend I have blinders on and I'm only looking at that small window, I don't care about the whole AB, but that small neighborhood, then that point is also the largest point in that small neighborhood. It's the largest for every X value near X naught, super close to X naught, in a very small window. And so it's automatically a local. Once it's bigger than everybody on the entire scale, it's going to be bigger than everyone in a small window where it's centered, right? So it's also going to be local, right? But we often don't label something both. If it's absolute and local, we usually label it just absolute. The local is going to be implied. So this is also a local minimum in that sense, and this one is also a local minimum in that sense. All right. Over here, similarly, at point A, that is our absolute max, absolute min up here, this point here is going to be our absolute max. In this point, again here, we have our absolute min. What will be the absolute max here?
Wouldn't infinity be the absolute max? So wouldn't it just be like a local max?
Right, but our absolute max, if you recall, we do need to identify an x value for that, right? So I need to be able to say the absolute max occurs at this point, right? For this x value, this is the output, and that is the absolute max, right? In the case that my graph goes to infinity, am I able to do that? What x value would give me infinity? There is no x value that would give me infinity. I want you to appreciate that this has no absolute max, right? Because the moment I pick an x value and I say, all right, that's the absolute max, you could take another x value to the right that gets me a bigger number. And then I go like, okay, that's the absolute max. You can take another x value to the right that gets you a bigger number, right? No matter what I say is the absolute max, you can take an x value closer to b to get an even bigger output, right? So we do not, this isn't like limits where we have infinity as a possible answer. We need to identify an input and the corresponding output. And it doesn't work when the graph just shoots up to infinity. Because what that means is you can inch closer to an asymptote with an x value, and you can get a bigger value. Right? So there's no x value in the interval a b at which the output at that value is greater than or equal to every other output. You can keep getting greater and greater outputs by taking x values closer and closer to b. Similarly here, this has neither, right? This is no absolute max nor absolute min. Okay. You could also say there's no local extrema here, by the way. There's no local extrema. Here also, there's no local extrema. Well, there's a local min. No local max. It's also a local min. This one has no extrema whatsoever. No local max, no local min. Okay, no absolute max, no absolute min. You look at this problem, and you can identify this part here as your absolute min. You can identify this part here as your absolute max. It's also a local max. And this guy is, of course, also a local min. But this one also has other local extrema. If you look here, that part is a local max. This part is a local max, right? This part here is a local min. This part here is a local min. Meaning if you zoom in very close to that point and just look at a small neighborhood around those points, they're the biggest guys around. This point here is a local min. Okay. So that's where the absolute extrema would occur and the local extrema would occur. This graph happens to have both. All right. Looking at this one. What's the absolute max? There is no absolute max. Right. What's the absolute min? Well, there are no absolute mins. Local maxes, local mins, sure. We have a local min right here. We have a local min right here. We have a local max right here. And that's it. Those are all the extreme points. I want you to appreciate that that cannot be a local max or an absolute max because the point doesn't even exist. There is no x value. Remember, it's very important that we can identify an x value. And sure, I can take x values very close to that and keep getting bigger and bigger, but I never actually get to a point where I'm the biggest, right? I can keep getting closer and closer to becoming bigger than the last guy, but I can never get to a point where I can say, oh yeah, I'm the biggest dude around, right? Similarly here, this guy cannot be either a local max or a min, because you might say, yeah, I can get to the biggest value on here. However, if I were to open a small window around him, notice that to the left of that, there are outputs that are larger than the shaded circle. So that also doesn't work, because if I open a small window where that point is the center, there are things that are bigger than that thing, and there are things that are smaller than that thing. So it doesn't satisfy either definition. So those are all the extrema. And hopefully that is somewhat makes things a little bit clearer. The absolute max and min is the biggest guy, right? So this is probably a nice illustration because you have both here, where you can see the local maximums and mins. Those are your little hills and valleys. The absolute max and min is the biggest hill, the deepest valley, right? And that's the difference. All right, cool. Hopefully that was helpful. Now, I want to get to the point where we can find these guys. It turns out the local maximums and minimums, we can actually find those using the first derivative test. So that's not going to be bad. But we need something else for the absolute maximums and minimums. So let's move on to being able to do that. Important theorems to know. You don't have to know how to prove them or anything, but you just should know them, what they say. Okay, so one, there's a theorem called the extreme value theorem. Which is an interesting one. Depending on the advanced math textbook you look at, sometimes this is given as an axiom. Sometimes it's not. There are many ways you can develop math. And yeah, so an axiom is something that you just take at face value. Everyone assumes it's true, and we don't care about a proof for it. But the extreme value theorem, very fundamental in that sense. Sometimes people just say, oh man, it's obvious. Why do we even ask for a proof of this? Like, this should be clear. But that is when you're kind of building up calculus from the foundations. So what this says is, if f of x is continuous on AB, then f is guaranteed to attain its absolute max and absolute min on AB. Basically, a continuous function on a closed interval is guaranteed to have an absolute max and min. it's not possible for it to not have one. So the max and absolute max and min must exist if your function is continuous. You would notice that in the situations where we did not have absolute extrema, it was situations with discontinuity. Notice in the first two in the top, we had all absolute extrema. Notice that they were also continuous. I could draw them without lifting my pencil off the page, all that good stuff. Didn't go off to infinity or anything like that. Whereas here, at B, now I can't draw through B without lifting my pencil off the page. In fact, I can't draw through B at all. Same thing with this part here. I can't, right? It is continuous, but not on the closed interval. It's continuous on the open interval, and that's very important, right? It's not continuous at A. It's not continuous at B, right? Because the function is not defined at A. It's not defined at B. Here, this one was continuous. It was defined at A, it was defined at B, and it was defined at all points in between. I had to be able to find an absolute max and min. Here, I could find neither. And that's because it's not continuous, right? Obviously, it's not continuous over here. There's a jump. There's a hole, right? So it turns out you are guaranteed to be able to find absolute maximums and minimums when your function is continuous. And this is just something you should know. Every now and then, I ask a question. I give students a function on an interval, and I ask them, find the absolute max and min. And every now and then, I would get a student saying, oh, there is none. I'm like, the function is a polynomial. It's continuous. There has to be both, right? There has to be. There's no way out of it. If your function is continuous on a closed interval, it must have an absolute max and min there, guaranteed, right? Okay, that's called the extreme value theorem. We are guaranteed to have extreme values in this situation. If we're on a closed interval and we're looking at a continuous function, there is an absolute max and absolute min. Believe it, right? Dr. Bayo. All right. Another important theorem. Make sure I get the Another important theorem is something called Fermat's theorem. Fermat. Not Fermat's last theorem, which is infamous at this point, was proven very recently in the late 90s by an Oxford, I think he's at Oxford, Professor Andrew Wiles. Really annoyed mathematicians for like 300 plus years. Fermat was not, he was an amateur mathematician, and he developed a lot of theorems. He's the guy who basically said, so we know Pythagoras' theorem, a squared plus b squared equals c squared. He basically said, well, all right, if you replace the 2 with n, where n is larger than 2, and a, b, c are integers, then positive integers, then no solution, right? It's actually impossible to find a triple. You know, like how we have 3, 4, 5 when n is 2? Yeah, such numbers cannot exist in the general case. So if you had a cubed plus b cubed equals c cubed, you cannot find integer solutions to that equation. Look forever, you will not find them. This was Fermat's last theorem. He wrote this theorem in the margin of his books, and he's like, oh, I found a really awesome proof of this really awesome statement that looks very simple, but it's actually quite complicated. It turns out you can't solve this equation with integers if your power is greater than 2. And it seemed like a very simple thing, because Pythagoras' theorem is remarkably simple to prove. You can find websites where they give you like 100 plus proofs of Pythagoras' theorem. And so to say, once we change those 2s to like 3s, now it's impossible. What are you talking about? Yeah, it turns out it took mathematicians 300-ish years to actually prove that that was true, where Fermat called it. But he didn't give a proof. There are people who don't believe he had a proof. Maybe it was just a guess. But yeah. But that's not the theorem I'm talking about. This is a theorem we actually know how to prove. It's called Fermat's theorem, and it says, suppose f of x attains a local max or local min at x equals x naught, and that f prime of x naught exists. So two things happen. We know that we have a local max and min, or min, right? So we know, okay, here's a local max. And at the same time, the derivative exists there, meaning if I zoom in, I can construct a tangent line that will look like the function locally. Okay, so Fermat basically said, then it turns out that f prime at that point must be 0. That's Fermat's theorem. If you have a local max or a local min, and the derivative exists, the derivative must be 0. Yeah, that's basically Fermat's theorem. It's actually not hard to prove. When I do the when I teach the 1206 version of this class, I actually prove it, and it's actually pretty easy. It's not like Fermat's last theorem, right? That's the famous one. Which, by the way, Fermat's Enigma is a very nice book about that. Which you don't need to be very mathematically literate to understand. I think it's actually a good read in general. Do I have it? Yeah, so that's the book. It's a novel. It's one of what you call a popular math book, where it says, there it is right there. No solution. Okay, so it's actually one of my favorite books that's not a textbook, which was pretty nice reading through that book. So yeah, you might be interested. All right, back to the matter at hand. Okay, now there are some very important things that we need to know about this theorem, because non-mathematicians often interpret mathematical language like everyday, oh, I'm talking to my friend language, whereas mathematical language is not like that. It's actually very precise. So it's very important that it says, if we have this, then that is true. And it didn't say it the other way around. So let me actually make that clear. Note, the converse of Fermat's theorem is not true. I.e., if we know f prime at that point is 0, it does not mean it's a local max or min. Okay. If we know it's a local max or min and the derivative exists, then the derivative must be 0. If someone told me the derivative is 0, they're not telling me anything. I do not know if it's a max or min. I can even give you an example. Look at f of x equals x cubed. We know that this guy has no local max or min, right? This is the graph right here for x cubed. Right? This guy has no local max or min. There's no hill or valley, right? It's kind of always on the ascension. However, but f prime of x is 3x squared, and f prime at 0 is 0, but we do not have a local max or min at 0. So just because your derivative is 0 does not mean you have a local max or min. And that's why in the first derivative test, I don't just ask you to find where the derivative is 0. I ask you to test a little bit to the left. Is it increasing or decreasing? Test a little bit to the right. Is it increasing or decreasing? Because just knowing that the derivative is 0 is not enough information. It's possible to not be a max or min, even though your derivative is 0. And that's very important that you don't assume that from Fermat's theorem, which a lot of people do, especially if you're not very mathematically experienced. There's another thing that's very important about this, and that is in the case where the derivative does not exist. In Fermat's theorem, we assume that the derivative does exist. I want you to make another special note. We may or may not have local extrema at points where f prime does not exist. It's possible to have a local max min at points where f prime does not exist. Does anyone know an example? We've actually touched on an example several times in this class already. Absolute value of x at x equals 0. We know that this has a minimum at 0. So here, notice we have local min. In fact, it's an absolute min. At x equals 0. But f prime of 0 is undefined for this function. It's a sharp corner. Okay. But Fermat's theorem actually does something good for us. It kind of indicates what points we should care about. So Fermat's theorem would help you to identify potential extrema, right? But obviously there is further checks that needs to be made. And this is what led to the notion of, which we've actually mentioned before, but I kind of defined it on the spot very hastily, critical points. You've heard that phrase before, and these points, it was critical that we could find them. And why was it critical? Well, it's because these guys is where we have the potential to have maximums and minimums. So definition, we say x is a critical number if critical number of f of x. If f prime of x equals 0 or f prime of x is undefined or does not exist. So that's a critical number definition. If x is a critical number, the point x comma f of x is called a critical point. Okay. You should note here the common vernacular. In practice, we sometimes call critical numbers critical points. This is technically incorrect, but it's understood in context. So in the past, when I told you, oh, find the critical points, usually what you looked for was the x value where the derivative was 0 or undefined. Technically, if I ask for a critical point, you're supposed to give me the whole coordinate. But often we just take the x value as the critical point, and we just know that we could find the coordinate if we wanted to. But so just be aware of that. Now let's talk about finding extrema, but we'll do examples next time. How do we go about finding extrema? Because it's going to be important. Well, if local, use the first derivative test. So we're done there. Or second derivative test. There's a second derivative way to determine this, provided the second derivative exists, but we did not cover it, not covered. It's superfluous if you're doing the first derivative test, which I'm usually going to require that you do, and it even gives you less information than the first derivative test. So we'll stick with the first derivative test. If absolute, you use what's called the closed interval method. Okay, so this is a new method I'm going to teach you guys by which you can find absolute extrema. So let me just tell you what that is. Okay. Suppose f of x is continuous on AB. We can find its global extrema. By the way, remember, these are guaranteed to exist. By the extreme value theorem. Let me put that in extreme value theorem, EVT. Here are the steps for the closed interval method. 1, find all critical numbers in AB and evaluate f at these numbers. 2, you're going to find f of A and f of B, right? So that's evaluate f at the endpoints. And then 3, you're going to compare. Above. And then, of course, you can make a conclusion. The largest y value, that will give you the absolute max. And the smallest y value will give you the absolute min. And it's important to check both, because from our examples above, notice that an absolute max or min can occur at the endpoint, right? So here you have the absolute max. If we look at this example, the absolute max happens in the middle between A and B, but the absolute min actually happens at A, right? So it's very important that you know what the outputs at the endpoints are as well, because the largest or smallest value can occur at the endpoints. It's possible. We normally state these as coordinates. So example, we say f of x naught equals y naught is the absolute max. So I don't just tell you the x value and I don't just tell you the y value, I actually tell you both. F at this value equals this output is the absolute max. So you'll kind of state it more generally like that. I'll leave you guys with an example that we will pick up with next time. Suppose f of x equals x to the 4th minus 4x squared. Find the absolute extrema of f on the interval -1 to 3. So I'll leave you guys with that to try. And we'll pick up with that next time. So absolute extrema guaranteed to exist here. This is a polynomial, it's continuous everywhere. So it's definitely continuous on the closed interval -1 to 3. And we can use this process to figure out what are the absolute maximums and minimums to that. And we can call these the absolute extrema. Yeah. So a lot of theory and definitions today, but we did get some problems, a related rates problem out of the way. But yeah, we'll do more examples next time. Make some more definitions, and we'll probably move on to curve sketching, which there's a handout on the class website about. But yeah, for now, we will stop there. That's it. Okay, hopefully that was clear. Thank you for your time and attention. We will wrap it up there, and I will see you guys in the next one. Ciao.